Is it clear? Normally, what happens is that if you have a ventricular septal defect, or you have a atrial septal defect, or you have a patent ductus arteriosus coming when there is the distinct communication between the two vessels, is it clear? You need to know that generally the left side of the heart, is stronger than the right side. Is it clear? So what happens is that at the beginning, blood that is supposed to be from the left side is going to shift toward the right side and go to the pulmonary circulation, and is going to perfuse one of the pulmonary circulation there, so there is not going to be any cyanosis. Is it clear? But afterward, since much of the blood coming from the left ventricle and the right ventricle are going to the pulmonary circulation, there's going to be congestion inside the pulmonary circulation. So the pulmonary circulation will not want to receive again excessive of those blood. What's going to happen is that there's going to be constriction of the pulmonary vessels, such as to reduce the circulation into the pulmonary circulation. And that constriction is going to result now to the right ventricle to overwork heart. Is it clear? So the workload on the right ventricle is going to increase. That is going to result now to a right ventricular hypertrophy. That is exactly the reason why you have a boot-shaped heart in the case of tetralogy of Fallot. The boot-shaped heart is a result of the right ventricular hypertrophy, because that right ventricle has hypertrophy and push the left ventricle upward such that it becomes a boot shape. Is it clear? And when that right ventricular hypertrophy, there's going to be now a shift of blood instead from the right ventricle to the left ventricle, and reducing perfusion of the lungs, which is going to now result to cyanosis. So that's how an acyanotic congenital heart disease can convert to a cyanotic congenital heart disease. So after that, now in the cardiovascular system that we have visualized, the congenital heart disease can be associated there. We have other elements, fetal abnormalities, which can be associated with birth asphyxia. In labor, is it clear? The fetal abnormality associated with labor, we have what is called a meconial aspiration. Is it clear? A meconial aspiration, which can be associated with labor. And we have also the fourth one, which is GIT. Is it clear? Now, meconial aspiration, which is associated with labor. So in labor, we need to know that what? We need to know that meconium in labor can show you two things. Meconium can either tell you that there is acute fetal distress, or meconium can be the cause of a birth asphyxia. So meconium can tell you that there is acute fetal distress, which that acute fetal distress is going to be the cause of the birth asphyxia. Are you understanding? That meconium can tell you that there is acute fetal distress, and that acute fetal distress is going to be the cause of the birth asphyxia. Also, the meconium can tell you that there is going to be meconial aspiration, and that meconial aspiration is going to be the cause of the birth asphyxia. So those are the two major ways in which you have to visualize, basically. In order to know that there is an acute fetal distress by the time of labor, you have to do now the cardiotocograph, or you have to use a cardiotocograph, or you have to use a parthogram. Is it clear? So those are the two major things that you have to use. You either use a cardiotocograph or use a parthogram in order to know that the acute fetal distress is going to be the cause of the birth asphyxia when there is a meconium. Is it clear? But now, if there is no fetal heart rate, if you realize that the fetal heart rate, because the elements of the parthogram, the major element of the parthogram is fetal heart rate. Is it clear? If the fetal heart rate, there is no fetal bradycardia nor fetal tachycardia on the parthogram, it shows that it is not really significant for an acute fetal distress. But now on the cardiotocograph, in addition to the fetal heart rate, we have other elements like the fetal heart variability, and we have also the fetal acceleration. Is it clear? Fetal heart variability and the fetal heart acceleration. The fetal heart variability refers to the change of the fetal heart rate within a period of time. Is it clear? There is a change in fetal heart rate within a period of time. Is it clear? Meaning that what? So that is just the fetal heart variability. The acceleration refers to the within a period of time. Is it clear? Now, acceleration refers to the rate of change of fetal heart rate. Is it clear? Within a period of time. There's a difference between the change of the fetal heart rate within a period of time, or the difference of the fetal heart rate within a period of time, which is the fetal variability, and acceleration, which is the rate of change of the fetal heart rate within a period of time. Is it clear? So those are the elements that you have to point. And the fetal heart rate refers to the number of heartbeats per unit time. Is it clear? So it means that what if you have your cardiotocograph, is it clear? You need to know that the fetal heart rate at one point can be 130 beats per minute. At another point, the fetal heart rate can be 140 beats per minute. Another point can be 135 beats per minute. So those are the different points that you have to know. Is it clear? So these are the instantaneous fetal heart rate. Is it clear? Now let's say that the time within which you are taking the different fetal heart rate is going to be 1 minute on the cardiotocogram. Is it clear? 1 minute. So that point in time is going to be 1 minute. Now let's say that you want to calculate the difference in fetal heart rate. That's the fetal variability in 1 minute. The fetal variability in 1 minute is going to be 140 minus 130. That's going to be 10. Is it clear? So the fetal variability in this case is going to be 10 in 1 minute. Why the fetal acceleration in 1 minute is instead going to be is a rate of change. It's not just the difference, the rate of change, meaning that what is going to be 140 divided by 110 divided by the time of the change. Is it clear? So it's going to be 140 minus 110 divided by the time, that is in minute now, instead in seconds. Is it clear? That's 60 seconds. Is it clear? So it's going to be 10 divided by 60, which is going to be give 1/6 beats per no, you instead put it in minutes, but because the unit has to be in minutes, in beats per minute. Is it clear? So in 1 minute. Is it clear? So it's going to be 1/6 beats per minute square. Is it clear? So 1/6 beats per minute square. So that is the fetal, what is called the fetal acceleration. So within 1 minute, there is going to be an acceleration by 1/6 beats per minute square. Is it clear? Now you have to know that what the fetal variability is the one which is the most precise in order for you as a cardiotocograph element, in order for you to diagnose fetal heart distress. Is it clear? While the fetal acceleration is going to help you to know the etiology of the acute fetal distress. Now you need to know that what preplacental etiology of acute fetal distress